Hello everyone, Paul here. Let's review for test 3. The review isn't very long. You can see it right here, and there's not that much for notes, so I think this ought not take too long. Alrighty, so first of all, we got meteorology, climate change, and beach erosion. Those are our 3 topics. Okay, so meteorology. First of all, what's the difference between weather and climate? Right there, right? Weather is the state of the atmosphere at a given time and place. Climate are those same conditions, but now averaged, right? And so, weather is just, it's hot outside. Climate is an average of the temperatures over time so that we can see how those averages change. Let's see, what's our atmosphere made of? We've got a nice little bit right here. Mostly nitrogen, 78% nitrogen, 21% oxygen, almost 1% argon, some carbon dioxide, and then random other things, krypton, methane, things like that. But there we are. There's the gases that make up our atmosphere. Now, along with the gases, there are some things that change from one place to another, right? We call these variable components. The gases aren't going to change. It doesn't matter where you are. Those are the gases. Variable components are right here. This includes things like ozone, which is O3. That's a variable component. Let me see if I can make it so I'm highlighting. There we go. Maybe not. Yeah, it is. Okay, cool. Water vapor, that's humidity. We live in Florida. We know all about water vapor. And then aerosols. These are tiny little droplets of oil or maybe some salts or something in the air that they're very important because they scatter sunlight. About 60% of the sunlight that hits the surface of the earth has been scattered. So when you step into a shadow, it's not completely dark and very cold because even if you're not in direct sunlight, you're in scattered sunlight. Okay, so let me see. What are the 3 main things that we measure in the atmosphere? And you should probably know what they are. So here we go, right? Humidity, which is water vapor in the air. We live in Florida. We know all about humidity. Temperature, it's hot, it's cold, it's temperature. We don't know what temperature is. And then atmospheric pressure, which is the weight of the air. Rising air is lower pressure, sinking air is higher pressure. Rising air is nasty weather, sinking air is nice weather. So generally, as I said in class, if you need to predict the weather and you can only know one thing, you want to know the air pressure. High pressure, nice weather, low pressure, rainy weather. Okay, let me see. There we go. Things we measure. We did that. What causes the seasons, right? It is not that we are closer to the sun in the summer or further in the winter. Okay, that is simply not true. What's happening here is what I just highlighted. The Earth's axis of rotation is tilted 23.5 degrees. So if you're in the hemisphere tilted toward the sun, it's your summertime. If you're in the hemisphere tilted away from the sun, it's your wintertime. And that changes throughout the year as the Earth goes around the sun, right? So here it's summertime in the northern hemisphere, wintertime in the northern hemisphere, and then the southern hemisphere is reversed. When it's summertime up here, it's wintertime down there, and vice versa. Alrighty, cool. Let me see. Temperature and moisture conditions of the different air masses. This is what controls a lot of our weather, right? And so we've got this little shorthand for air masses. Anything with an M stands for maritime, and it's going to be wet or humid. Anything with a C stands for continental, and that's going to be dry or not humid air. Anything with a P stands for polar, that's going to be cold. And anything with a T stands for tropical, and that's going to be warm, right? So maritime polar is wet and cold. Continental polar is dry and cold. Maritime tropical is wet and warm. Continental tropical is dry and warm. And I don't think you need me to tell you that this is what we usually have sitting over us, which I just unhighlighted. There we go. Okay. Describe winter and summer weather patterns in Florida. And so remember that the winter time pattern is, warm temperatures followed by rain, followed by cold temperatures, right? And the reason we have that is because this pattern is dominated by cold fronts, right? This continental polar air moves in, it shoves that yeah, sorry. I'll say it right. I did say it right. This continental polar air comes in, it shoves that maritime tropical air out of the way. That leads to condensation and precipitation and rain. And then behind it, you have that nice, clear, high pressure weather that we all love so much in the wintertime. Summertime pattern is there, right? Highs in the mid to upper 90s, clear in the morning, scattered afternoon thunderstorms. I'm recording this in the summertime, and that is exactly what we're getting now. Exactly what we're getting now. And so what happens here is, as I say over and over again, the sun doesn't heat the air, the sun heats the earth. That warm air rises. As it rises, it cools. That leads to condensation, precipitation, and those afternoon thunderstorms that we all know and love so much. So there we are with weather patterns, and that's 7 and 8, describing the weather patterns and what causes them. Dealing with climate change is some very, very simple stuff. First of all, how is the Earth heated? And here it is right here. And I've been beating this into your heads for days now. I think, once again, the sun doesn't heat the air. The sun heats the Earth, and the Earth heats the air. So short wavelength radiation, that's light, reaches the Earth. Most of it passes right through our atmosphere. Let's face it, you can see through our atmosphere, right? That radiation hits the surface of the Earth. It is absorbed and re-emitted as heat, and greenhouse gases trap the heat, right? It's that simple, really. And so, yeah, let me see. What are the feedbacks that are causing the Earth to warm faster than we thought, right? Because here's the problem. As we add more carbon dioxide to the air gets warmer, right? When you add more heat-trapping gas to the air gets warmer, and we're adding 70 million tons of carbon dioxide per day, okay? And the Earth is warming, and it's warming faster than we thought it would. So why is that? Well, first of all, so what are those feedbacks? And that's question number 10. Albedo, right? And this has to do mostly with ice, right? Ice makes the planet cooler. Not because it's cold, but because it reflects sunlight. And so as we melt ice, that makes the planet warmer, which causes more ice to melt, which makes the planet warmer, which causes more ice to melt. And you can see how that's what I mean by a feedback, right? It's something that kind of spirals on itself. And so there is that. More feedback. Sorry, water vapor. Water vapor, right? As the Earth gets warmer, we evaporate more water, and water vapor is a powerful greenhouse gas. So, yeah. Water vapor will come out because that's, rain, but as long as it's there, it's contributing to the problem. Methane, oh boy. As we melt permafrost and other things, we release more methane into the air, and methane is a very powerful greenhouse gas, and no one's really sure how you get it out. So that's kind of a problem. So that combination of the ice melting, changing the planet's albedo. By the way, albedo is just a fancy word for the amount of sunlight a planet reflects, or a surface reflects. So yeah, and I should highlight that again. Anyway, there we go. Okay. Albedo, water vapor, and methane are the three main feedbacks. And then, okay, so let me see. Feedbacks and then consequences of a warming Earth, other than just heat, right? So here we go. Here they are. I brought them down for you, and I'm going to go and highlight consequences here. Sea level rise, something we have to deal directly with here in Florida. More weather-related disasters, hurricanes, floods, droughts. I mean, we call it climate change because the effects are actually different everywhere. Overall, the planet is warming, but what that means in different locations varies from one location to another. Animals migrating, ecological decoupling, where an insect migrates and it loses its plant, and so now the insect and the plant are in trouble. And then fires, more fires, longer fire season, more fires. We're burning through, our entire firefighting budget in like the first 3 months of fire season now. It's really insane. Okay, so there's that. Those consequences, that's consequences. And as far as our response goes, there's three things. Prevention, which is keeping it from happening. That's too late. It's happening. So we can't prevent it. Mitigation is just the idea that, okay, maybe we can't prevent it, but we can always make it better, right? And yeah, we can. That's absolutely true, right? And so there's some things underneath there, but mostly I'm worried about the top line stuff here. And then adaptation, right? This is where we are, right? Learn to live with it. It's happening. It's happening. The degree to which we're going to be able to mitigate it is, an interesting question. It's just happening. And so, how do we live with it? How do we live with it in an intelligent way, minimizing the damage from it as much as possible? Never, ever, ever give up on this. Never, ever, ever give up on mitigation, but understand that adaptation is going to have to happen too, and it is utterly too late for prevention. That's just that window has closed. Okay, cool. Okay, so let's do beach erosion. So what are beach drift and longshore current, right? And here they are right here, right? Let me see that. Let's go up here. Actually, there we go, right here. Beach drift is sediment being moved by waves breaking on the shore, right? So, a wave comes in and moves sediment down the beach. The sediment goes back toward the water, and then the next wave comes in, right? And so it kind of zigzags its way across the beach. That's beach drift. Longshore current is that current right there in about 4 or 5 feet of water, right there at the shore, that moves parallel to the shore, right? Both of these move sand, and that sand can be a problem. So then I ask, okay, what's the effect of longshore current on barrier islands? That's question number 14. And so here we go. Barrier islands move, right? The longshore current removes sand from the upstream side, it puts it on the downstream side, and so that entire barrier island moves by several feet a year. This is not a millimeters kind of a thing. This is something that's happening at a rate where we cannot ignore it. Okay, so let me see, blah, blah, blah. Placing jetties at inlets, right? So in order to stop that movement, we build walls out into the water called jetties. Usually we just pile up rock out into the water. That's a jetty. That stops the longshore current. And so what ends up happening is you end up depositing sediment on the upstream side of that jetty, right? The problem is on the downstream side, where your beach is suddenly starved for water. Or, I'm sorry, not starved for water, plenty of water, starved for sand, right? And so you get erosion on that downstream side. And so you want to be really, really careful what you do on the downstream side, right? You don't want to build condos too close to the water with seawalls. You don't want to do that. You want to give that beach space to kind of move around a bit and settle into that new regime with less sand. Okay, so there we go. Jetties. What are 2 reasons sea level is rising? Here we go. And actually, I have a bit here. Let me add something here. And I'm gonna pause this, and then it'll be back, and then you'll have it in your mailboxes when I send it to you. Magic how that happens. I've got a little more notes, and I added a question to the review sheet. So, but not a big deal. So anyway, so I ask here, where am I? I ask, what are the 2 reasons sea level is rising? And now that is in the notes. Sea level is rising because, first of all, yes, glaciers are melting, right? We're melting ice on land. As the planet gets warmer, that's a problem. The other thing is, as the planet gets warmer, the water is simply getting bigger. Everything expands when it gets warm and contracts when it gets cold. And when you heat seawater, it gets bigger. So, yeah, and so it's lapping up on land. So both of those combine to mean that, yeah, sea level is indeed rising. And then this was a question that I added because it's important, and I'm going to turn it green or something like that, just so that green's not really a good color. Well, fine, we'll just turn it green. Okay. And that is, what does it mean that a beach needs to come into equilibrium, right? And I went through this in class, and so the idea here is that it's not just that the water's rising, right? It's that once the water rises, it chews its way inland to kind of get the slope back that it wants, right? When you see pictures of beach erosion, it's not that the houses on the beach are flooding. It's that they're being undermined by the ocean. And so, yeah, the water level comes up and then it goes in, and that in is the coming back into equilibrium part. Okay, I'll keep it green, but whatever. Okay, what is the effect of placing seawalls, groins, and breakwaters on a beach? Okay, so here we go. So we can look right here, and we see seawalls. Seawalls cause beach erosion, right? Seawalls, you know, they don't. Sorry, I don't know how to say this. They cause beach erosion, right? You put a seawall up, and you don't have any beach in front of the seawall, right? The minute that water touches that wall, the beach is gone. It just is. So I mean, ask yourself as you drive around Pinellas County, how often do you see, you know, a seawall with any beach in front of it? And you don't. It's almost always straight to water. Let me see, seawalls. Let me see. Let me go back here real quick. Groins and breakwaters. Okay, so groins is just a wall, going out into the water. A jetty is at an inlet. A groin is the same thing, just not at an inlet. So you just got beach and a pile of rock going out into the water, right? Does the same thing a jetty does, though. It traps sediment on that upstream side, causes erosion on the downstream side. Same thing with breakwaters. Breakwaters are walls running parallel to the beach. Same thing. It shuts down the wave energy, and so it shuts down the longshore current and the beach drift, so you get sand accumulating on the beach. The problem is sometimes downstream, where they don't have sand because you have all the sand upstream, and so you end up sometimes having erosion problems on that downstream side. Okay, so let me see. So there we go. See, blah, 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 blah. Beach renourishment. What are some of its issues? So here we go. Renourishment. Here it is right here. It's sometimes called, sometimes called just nourishment too. So if you see someone talking about beach nourishment, it's the same thing. It's pumping new sand on the beach, right? If the problem is there's not enough sand, let's add some sand. There we go. Problems, it's expensive, at least $1 million a mile. It's tricky to get it right. It is an engineering thing. You need people who know what they're doing. It's not as simple as let's just pile up a bunch of sand on the beach. It is not that simple. Tricky to get it right, and it's temporary. Even a good renourishment project is temporary. The beach is going to chew through that. The water, rather, is going to chew through your new beach. The question is, how quickly is it going to chew through the new beach? But it will chew through the new beach. And so it's temporary. And then finally, we have soft stabilization, which is just using natural materials on your beach, right? And so this is great for maintaining a beach, but it will not save it. If the beach is, having issues, if you're having to deal with hard structures causing erosion, soft stabilization probably won't be enough. This is a way to maintain a beach and prevent beach erosion. It will not reverse it. So this is like, planting sea oats, planting seagrasses, putting shells on the beach to armor it, putting driftwood on the beach. It all looks very pretty, very natural, and it's very good for maintaining a beach. But like I said, if your beach is too far gone, it's not going to work. It's just not going to work. Okay, there's the review for the third test. I'm going to go write the test. I will get as many questions as I can. All right, y'all take care. Bye-bye.